All right, so continuing on from yesterday here, okay, we had finished off talking about gravitational potential energy. Okay, gravitational potential energy is part of mechanical energy in this way. All right, mechanical energy is the sum of an object's potential energy and its kinetic energy. Okay, so the potential energy, or at least gravitational potential energy, is dependent on these three variables that we talked about yesterday. Mass, which is going to always be measured in kilograms. Okay, the acceleration due to gravity, which unless you're told otherwise will be 9.81 meters per second squared. Okay, and the height of the object above ground level, okay, because obviously you can't fall any further than that. All right, so those are our variables for calculating potential energy. We simply multiply them together. Okay, when we do that, we'll be taking mass in kilograms, multiplying it by acceleration, which is in meters per second squared, and multiplying it again by meters. Okay, so the units are kilogram meters squared per second squared, abbreviated as joules. All right, so that's what we would get, okay, if we were performing a calculation like that. All right, is that ringing a bell from yesterday? Okay. So if we're looking at kind of a simple gravitational potential energy problem, it might look something like this. A 3 kilogram box is lifted by an upward force 1.5 meters above the surface of the Earth to the top of a table. What is the potential energy of the box in its new position? All right, so we're trying to find potential energy. We're told the mass is 3 kilograms. We always know what G is because it says Earth specifically in this question. And it says that it's 1.5 meters above ground level, right? So all we have to do is plug in our numbers. 3 times 9.81 times 1.5, and we would find that this box now has 44.1 joules worth of energy. Now, incidentally, it now has that much energy. How much work did you do to lift it there? That much, exactly. Remember, we said yesterday that work is a change in mechanical energy. On the ground, that box would have 0 energy. Okay, so if I've done work to lift it to the top, okay, I have done the amount of work by which, or equal to the energy that I changed in that particular object. All right, so I've changed the object's energy by 44.1 joules. That's how much work I did, okay, because I transferred that energy to the box while doing work on it. Okay, questions there? Okay, another one that might require us to do a little bit of manipulating of that formula, okay, would be that we're told that we have a 55 kilogram diver standing on a diving platform, and they have 5,400 joules worth of potential energy. Okay, what is the height of the platform? All right, so we would take, and I'll just kind of walk through this so you see it done here. So EP equals M times G times H, right? And I'm trying to find the height of the platform. So how do I move? How do I get H by itself? All right, I divide M and G. I leave H where it is. Okay, and now I'm solving for H. Everybody all right with that? Okay, if I want to move something, I do the opposite. Do what I do to both sides, okay, and then I plug in my numbers. 5,400 joules, okay, divided by 55 kilograms, that was the mass of the diver, times 9.81, and we should get that it's the 10-meter diving platform. Okay, that's the tall one. Everybody all right with that? Okay, not an overly difficult formula to use, right? Everything's just being multiplied, so to move anything, you just divide. Okay, now, potential energy is all well and good, but it's only potential. Potential energy won't do anything until it's converted into kinetic. Okay? It's kinetic energy that does work. All right, it's all well and good to hold a brick above something, but it's not going to do anything unless you drop the brick. Okay, and then when you drop the brick, that potential energy turns into kinetic. All right. Speaking of bricks, and stuff like that, I'm going to show you a couple of videos, okay, of people using kinetic energy to do work, to break stuff, because it's kind of cool. Okay, so I'm going to show you, first off, these, there must be a martial arts club somewhere in China, okay, and they're just demonstrating all their ability to break boards, okay. Some of it is rather impressive. Some of it is more difficult to watch. There's an elderly fellow who fails to break the piece of wood several times. You have to watch this poor old guy keep hitting the wood. He doesn't quit. Like, to his credit, he won't quit, but it gets a little hard to watch this poor old guy smashing his knuckles on the. Okay. But we'll watch those two, and then we'll talk about how that's converting kinetic energy into other forms of energy. So we'll have a look at that. Oh no, then it's breaking one big piece of concrete. Nobody's going to do that. Okay, so you can see in this picture here that there's little spacers between the boards or whatever it is that this guy's breaking. Okay, and that's absolutely essential. If you don't have those spacers there, you're breaking one big thick piece of wood or one big thick piece of concrete, and nobody's going to do that. Okay, so we have to have that little bit of space in there in order to make sure that our energy is still able to pass through. Okay. Now, as Felix mentioned, there's you gain a bit of an advantage once you get through the first few blocks, because now it's not just your energy, it's also the extra mass and energy of the blocks you've already broken. They're trying to move downwards because you're pushing on them. So essentially, it increases the mass that you're using to push on the other blocks. Okay, so it kind of creates a chain reaction. I'm not saying that, well, so he only had to break 2. No, he had to break 27. Okay, but he has to, to get through the first 2 or 3 is still very difficult. All right, so we'll have a look at that one. All right, so if you're going to accomplish either of those 2 feats, okay, what are the 2 things that are part of the energy that you're using to do that? I talked about one of them, how when you break a couple of these bricks, you get more of this mass. Okay, mass is important. Okay, and what's the other part? Not so much the potential, because remember, potential doesn't do anything unless it's turned into kinetic. What's the other part of kinetic energy? Speed. Okay, those are the 2 things you need, mass and speed. Okay, speed being the more important part, because in the formula for kinetic energy, speed is squared. Okay, so we have EK equals 1/2 times the mass times speed squared. Right? So if I double the mass, I'll have twice as much energy. If I double the speed, how much more energy will I have? 4 times. If I triple the speed, I'll have 9 times. Okay, it's an exponential relationship. It's something that people don't always realize, okay, that there's an exponential relationship with kinetic energy and speed. And what that means for us in the real world is the faster I go will require exponentially more stopping distance. Okay, if I double my speed, I will need 4 times as much room to stop. Okay, and the reason for that is this. If I have kinetic energy, in order to stop, I have to exert a force over a distance. My brakes are only capable of exerting a certain amount of maximum force. So the F number is fixed. It's D that can change. Okay, and if I make V bigger, D gets bigger exponentially as well. Okay, so if you have, let's say, an idiot who's going 60 through a playground zone, he will need 4 times as much room to stop as a person going the speed limit. That's a lot. Okay, I'm going to show you what I mean here. I'll show you the math of it. So let's say going through the playground at the speed limit. Okay, so I'm going to say the speed of the car going through the playground zone is going to be 8.3 meters per second. That's 30 kilometers per hour. Okay, let's say the mass of the car is 1,500 kilograms, and the force that the brakes can exert, we'll say, is, I don't know, 5,000 newtons. Just to pick a number. All right, so those are the numbers that go with this car. If I want to stop, I have to take all of my kinetic energy and I have to turn it into something else. What do your brakes turn it into? Yeah, heat. Okay, they use the force of friction. So that F there is the force of friction. Okay, and they turn it into heat, sound, and anything but movement. Okay, we want to stop, so we're trying to turn it into other forms of energy. All right, so if I want to calculate how far it will take me to stop, what do I have to do with F? Divide it over to the other side. Okay? It's actually a very simple calculation. Right? This will calculate the stopping distance, okay, for a vehicle as it travels. So I'll plug in my numbers here. 1/2 times 1500 times 8.3 squared, so that's the speed, okay, divided by the 5,000 newtons worth of braking force the car can exert. Okay, so 0.5 times 1500 times 8.3 squared, okay, divided by 5,000. All right, so it takes 10.3 meters for a car going the speed limit to stop. To give you an idea, this room is about 10 meters wide. Okay, that's a long way if a little kid runs up in front of you. Okay, and that's going the speed limit. Okay, if somebody is going twice the speed limit, they're not going 8.3 meters per second, they're going 16.6. Okay, so let's plug in all these numbers, but with 16.6 in there. So 0.5 times 1500 times 16.6 squared divided by 5,000 newtons. .41 meters. Okay, that's roughly the length of the science wing. Okay, like from the doors here to the end. Okay, so they doubled their speed, but now they need 4 times as much room to stop. Okay, there's an exponential relationship. Now, not too many people are stupid enough to go twice the speed limit through a playground zone, but you guys are kind of new drivers. Probably not many of you have your driver's license yet, but we all tell ourselves that, oh, well, I'll just go a little faster than the speed limit, right? Everyone's like, and how much faster do we usually justify in our minds? 5 or 10, right? Because 10's not that much. 40's not that much different than 30, and we tell ourselves that, okay? We tell ourselves that 40's not that much different than 30. Well, 40 kilometers per hour in meters per second is 11.1 meters per second. Sorry, times 1500. Okay, so this is how far it'll take you to stop. How much further do you think it'll be? 20 meters? Okay, it's nearly double. Okay, that 10 kilometers an hour that we justify in our heads all the time nearly doubles your stopping distance because of that exponential relationship between speed and energy. Okay, it doesn't take much to really increase how far it takes you to stop. Okay, so you guys are going to be driving soon. Keep that in mind. Okay, that 10 kilometers per hour isn't worth it. Okay, and I'll show you mathematically why it's not worth it. Okay, it's not worth it mathematically because let's say I'm going through a 400 meter long playground zone. Actually, that's pretty short. Let's say the school zone would probably be about 600 meters long. Okay, so if I go 8.3, so I have a 600 meter long playground zone, and I go through it at 8.3, that'll take me 72.2 seconds. Okay, I'm saving myself how much time? 18 seconds. Guys, if that 18 seconds is the difference between you being on time or not, leave earlier. Like really, it's 18 seconds. Okay, we justify that. Oh, the 40 kilometers an hour, I got to go that 10 kilometers an hour faster because it'll save me so much time. No, it won't. Okay, and it's the difference, guys. That 18 seconds is the difference between me having dinner with my kids tonight or planning their funeral tomorrow. It's dark, but it's true, and people don't realize it. Okay, and what makes it even worse is the people that do that are also the people who aren't paying attention in the first place because they're on their phone when they're driving, which is like the worst thing you can possibly do. Okay, which is more dangerous, drunk driving or texting and driving? Yeah, texting and driving is more dangerous. You're worse than a drunk. I'm not saying it's okay to drink and drive, because it's certainly not, but a drunk will react. person who's distracted will never see it coming. Okay? I actually saw one in the Westmount school zone back in early September. There was a police officer running a speed trap in the school zone. And this lady was barreling through. She must have been going 55 in the school zone. He stepped out to stop her. She was on her phone. He had to dive out of the way to avoid being hit by her as she sped through a school zone as school was being let out. There were children everywhere. I have never seen a police officer so mad. Okay, like, yeah. I'm sure she lost her license, like she should have anyway. Okay, like there's just no excuse for that, guys. Put the phone down, pay attention. Okay, has anyone ever showed you the difference in reaction time? Okay, I'll do this as a cool demo. Okay. Oh, absolutely. Yeah, and they go into the windshield. Yeah. Okay, so a couple of things here, guys. So the big thing about kinetic energy is that it's energy due to motion. If you're not moving, you don't have it. Okay, and we've already talked about how speed is exponentially related to how much kinetic energy you have. Mass is linearly related. That means if I double the mass, I'll have twice as much energy. Okay, when we have something like a roller coaster, okay, we're taking those two forms of energy and we're turning them into one another. You get towed usually to the top of the first hill, and then you have lots of potential energy. Then you roll down the first hill, that potential turns into kinetic. Okay, you go back up here, the kinetic turns back into potential, and so on. Okay, if there were no places where you could lose energy, you'd have the same amount of mechanical energy everywhere on the ride. No, you'd have the same amount, whatever the number, not zero. Okay, so if I'm up here, all of my energy is potential. If I'm down here, most of it is kinetic, and so on. It just gets converted back and forth. We call that the law of conservation of energy. Okay, everywhere on that ride, I would have the same amount of mechanical energy. I wouldn't have the same amount of kinetic and potential because they're constantly turning back and forth into each other, but they're always preserving the value of their total. Okay. All right. Okay, so thermal kinetic energy is a bit different. Thermal kinetic energy is what we measure with temperature. Okay, so temperature is not a form of energy. Temperature is a measure of the thermal kinetic energy of the particles in a substance. So if I put a thermometer in a glass of water, okay, it gets hit by the moving molecules that are in the water. Okay, the hotter the water is, the faster those particles are moving, and the more often they run into the thermometer and transfer energy to it. Okay, the more they hit it, okay, the higher up the indicator, which is usually alcohol, goes inside the thermometer. Okay, everyone kind of follow me there? If they don't have a lot of energy, that is, it's quite cool water, then when they hit the thermometer, they don't hit it as hard, and they don't transfer as much energy to it, so they don't cause the indicator to move up nearly as far. Okay, everyone kind of follow me there? So we're turning kinetic thermal energy into essentially different kinds of energy as it hits the thermometer. Okay, the thermometer just indicates to us how fast the particles are moving, so temperature is a measure of the thermal kinetic energy of a substance. Okay. All right, so we were looking at this formula here just a minute ago. Okay, so we've got mass in kilograms, speed in meters per second, and look what we get for units when we use that. So we got kilograms, and we're multiplying that by speed squared. Same units we got before. Kilogram meters squared per second squared. Okay, so it comes out to joules in that case as well. Oh, see, this is from last semester. Did the same demo. All right. Okay, I want you guys to try this one. Okay, in this one here, it's similar to what I showed you with the braking. Okay, we're going to be saying that the work, actually, let's do this one together. I'll give you a second to write it down, and then we'll walk. Okay, so this is kind of a classic work energy theorem problem. In this question, I'm doing work on the rubber band. I'm changing its shape. Okay, I'm making it stretchy. I'm stretching it longer. Okay, in order to do that, I have to exert a force over a distance. Okay, and so we know that the formula for work can be force times distance, but it can also be the change in something's energy. So in this case here, if I have this rubber band and I stretch it, okay, and I put a ball in it, so essentially I make it a slingshot, right? All the work that I do will become what for the ball when I let it go? become kinetic energy. Okay, so essentially what we're saying in this problem is that the work I do is going to be equal to the change in the kinetic energy of the ball. Everyone with me so far? Okay, all I'm saying here right now is that work is a change in energy, okay, which is the work energy theorem. So if I want to calculate the change in kinetic energy, that's going to be force times distance equals 1/2 times mass times the final speed squared minus 1/2 times mass times the initial speed squared. Except what was the initial speed? 0. I'm holding the ball in the rubber band. It has no initial speed. So this whole thing right here is 0. Okay. So then I'm left with this, exactly what I had before when we were talking about how long it takes to stop in a school zone. The work, the stretching of the rubber band, equal to the kinetic energy of the ball when I let the rubber band go. Okay, now again, this is in the perfect physical world. In the real world, not all of this work is going to become kinetic energy for the ball. Some of it will become sound because I'll be able to hear the rubber band snap. Okay? There'll be some heat generated and things like that. In the real world, it doesn't all go in here, but we simplify things. We say it's all good. Okay? Everything obeys the laws of physics perfectly. Okay? All right, so now I want to calculate the speed at which this leaves. We'll talk about that on Monday. Have a good long weekend, guys. We'll see some of you tonight.